Testing, testing. Testing. I'm still testing. That's testing. Wow. Okay.
Yeah. Can you see my slides now?
Yes, I can see them.
And you can hear me okay. And hopefully the room can as well. Okay,
Yeah,
that's good.
Mark said he was connected.
One, two. Right.
Hello? I heard a 1, 2 there.
Oh, that's Brad. Hello, Brad. Everything seems to be fine here. We're going to start the session in a few moments.
Okay, I can barely hear you.
Okay, how about that?
Yes, that is better.
Okay. I think it's time.
I still can't really hear much in the background. It's just a very faint, almost inaudible voice. I presume that was Mark.
Here, Bruce, is everything okay? We haven't got the speaker mic, the actual speaker mic on yet, so. But Bruce, we're planning your presentation to be as a video.
One. 1. 2.
Yes,
3.
we can hear you.
Okay,
4.
thank you. We
Hello,
actually had
everyone.
a
Please
small
take a
issue
seat.
with the
There was a little
with
power interruption, and we plan to get moving in just a couple of minutes for the session the parallel session 3B. So just a couple of minutes. I wait for the thumbs up from the technical people, and we will get the slides going and have the session. I'm just waiting for the thumbs up from the technical people about projecting our slides. If you're online, please just be patient. We had a little technical interruption here. So we hope to be up in just a couple of minutes, waiting for the slides to become available. And we can have this one as well? Okay. Welcome, everybody. This is the Division B Parallel Session 3B. We've have this special location here in the exhibit hall. We're just waiting for the slides to become available through the system, and then we'll get going with the session. But perhaps I can just say a few words of welcome already. So my name is Mark Allen. I'm from Strasbourg in France. I'm the director of the CDS, the Strasbourg Astronomical Data Center. And I'm pleased to be chairing this session, which was originally organized by Bruce Berryman from Caltech, IPAC. And Bruce, unfortunately, was not able to be here, and I was very happy to step in for him. We have a session that's been part of the Division B days, and it's called Community Engagement, Open Science, and Virtual Observatory. And we've prepared a program for you with a number of speakers from different parts of the world, talking about different aspects of all of those different things, because it's one of the places, I would say, where astronomy converges. We have the data from the telescopes, we have the information from the publications, we have services online, and we're all trying to make those work to the benefit of the astronomy community. And so those three aspects, virtual observatory, which is a system of standards that enables us to share data, open science, which is a kind of new term for what we do about data sharing and all of its different aspects, and community engagement, where we're really making sure that the young people are engaged with the system. And so I can see I got a thumbs up now from the technical people, and I think we're able to go to the very first set of slides from, so I'd like to welcome Priya Hassan to the stage to tell us about the virtual observatory and education. I'm going to give the speakers a 3-minute warning before the end of the time. Each talk is actually a different amount of time in the program, so please take attention to that. I'll give you a 3-minute warning. We have a time for some short questions afterwards, and if we manage, we will bring the speakers together at the end. But without any further ado, let me ask Priya to come to the stage.
Thank you, Mark. Oops, 1 minute. Oh. Okay, this is magnetic. No. Hello? Yeah, is that good? Am I loud enough? Yeah. Thank you. So thanks a lot, Mark. And I hope I'm loud and clear enough for everyone. So I think this is better. Okay, great. Okay. So hello, everyone. I'm Priya Hassan, and I teach in the university in India. So I teach physics as well as astronomy for undergrads, for postgrads, as well as my PhD students. So what I've basically been talking about today is the VO and education, because especially during the pandemic, can people hear me? Can people hear me or not? You can hear? Yeah? Yeah, okay. Okay, fine. Okay, yeah, thank you, yeah. Okay, so I'll be talking about VO and education and how data accessibility in developing countries and access by underprivileged groups within developing countries can actually do the job of astronomy education. So I'll go on with it. Oops, sorry. Yeah, so that's the abstract that I had submitted to the IVOA. And basically what I'm talking about is how virtual observatory can be very well used as a tool for education, basically not only in astronomy as well as in data analysis and statistics. We had various projects, rather 2 projects from the OAD, which started one in COVID and one was post-COVID, which was basically using archival astronomy data. After which we had another project from the Virtual Observatory and OAD, and that was about spending 3 weeks in Copperbelt University, Zambia. This was basically to set up their master's data analysis lab. Okay, so what we did is we set up a set of 12 experiments, which we trained faculty and students with in Copperbelt. And we were hoping that the manual would be released over here, but it's taking a little longer. So we hope by the end of this year, we'll definitely finish the manual, and that would be released. And that can be used by astronomy departments all over the world, because they're basically using astronomy archival data with which they could actually be, they could be trained. So let's start about it. We all know that we lived in an era of multi-wavelength astronomy data, and there are various ground-based, space-based telescopes which are being used. And what I really like about is the paradigm shift. You know, earlier astronomy was more hypothesis-driven, where you had a hypothesis and you did observations to check your hypothesis. But now, essentially, it's a data-driven science, where the data actually speaks, right? We have so much of data about different objects, and therefore now I think a smarter way to do the science is to actually use your data to create your hypotheses, your understanding, so that you can understand the subject better, because you already have so much of data and so many objects to deal with. So, I should also mention it that one of the things we've been focusing on in our projects is that astronomy tools, people who know how to code or know how to handle statistics, or it could be even machine learning or whatever, it can be used by the student for application into any job, right? You could actually move to the industry. You could be working in any other place for the simple reason that you've developed the skills. So what our focus is more on, not just about developing your skills as an astronomer, but basically developing your skills as a kind of data scientist, where you can actually apply your skills to anything else. And this is basically because the number of jobs available in the astronomy stream is limited. And the idea as teachers, we are also concerned about the future of our students, right? The student should get placed somewhere. And therefore, if he or she develops skills with data on how to handle data, then it can always be used for the industry or something else, any other application. And I would say there's nothing wrong in applying it to anything else. So that's the thing. So that's our team. You can see my husband over there. And we've been working together. It's a two-man army. We've been doing things together. And he's also a professor at the university, teaches mathematics and astronomy. I teach physics and astronomy. And hence, we do a lot of our things together. It's easier to fight at home and sort it all out before you present it. So that's a good deal. Okay. So like I mentioned, the story started off with when the pandemic hit and the OAD started off, they kept a call out for proposals. These were for short-term proposals, 6-month proposals, because nobody knew how long the pandemic would last. And so we actually applied for it. We got it for archival data with astronomy. And we had applications from all over the world, because I think the good part of the pandemic is that it opened the online world, where people were now open to the idea of online participation, etc., which has definitely made a big difference, especially, for example, for me, where you are working in India, and you may want to attend a lot of conferences all over the world, but because you have an online access, you can, right? And it's obviously not as good as the offline experience, but it at least gives you some part of it, right? So this was the project which we started off, which was called Astronomy from Archival Data, which was funded by the OAD. We had 915 participants. We had it from all over the world. And we had our website where we actually, this thing. So what we did is that our modus operandi was that we had classes on every Saturday, Sundays. And the good part was that most students did not have classes. So they were free at that time. So on Saturday, Sunday in the morning, we would have our sessions, which were immediately live streamed onto onto YouTube. So people whose time zones did not agree with this, they could always log in whenever they wanted, and this thing. And we also kept the interaction on through social media, through Telegram, emails, Facebook, etc. And we had a variety of speakers for our program, which was not just us. We had Mark Taylor, who's done TopCat. We had Sushant Konard, an Indian astronomer who works on pulsars. We had Ruiza Rubil, who's from IPAC, infrared. We had Bruno Marin from ESA. And we had a whole bunch of people. You can see their names over there. And they were all presenting different areas of research. And the idea was that after the presentations, after 3 months of that, then people actually got onto projects, where they actually worked on projects. The second project which we got from OAD was called AstroSprint, and this was in 2022. So we were not sure about how many of our workshops would be offline or online. But since the pandemic continued, we had only two online workshops and one offline workshop where we did our stuff. And this is some pages of our website. And then this is the third workshop which we had, which was the offline one, which we had in India, which was this thing. And what we did is for all our projects, all the programs, everything got recorded and immediately live streamed onto YouTube, so that people could immediately access it and work on it, right? We also worked with LCO, which is the Las Cumbres Observatory. They have a whole suite of robotic telescopes. So the idea was that students should actually have the experience of observing, which they did with LCO. And in that, what happens is students get trained on even the simple thing about visibility. If there's an object they're interested in, when is it going to be visible? However, what LCO has is they have a scheduling process, and since they have 26 telescopes all over the world, they can observe your object from wherever. But the student can at least interact with the system and see when is their object observable from different locations, so that they can, number one, plan the object. They can plan their exposure times. They can plan their filters. They can plan various other things during the observations. And we actually give, even now we do that, we give students a free hand at actually putting up their own observation schedule. And even if they make mistakes, no problem. They can actually learn from their mistakes and try to schedule their observations and observe the observers they want to do. The interesting thing about LCO, we have another presentation about that on the 15th in the FM10. So the interesting thing about LCO data is that after you finish your observations, you can download the raw data and use it for normal CCD processing and do things like that. As well as LCO also has what is called a Banzai pipeline. And the Banzai pipeline already gives you processed catalogs and other data, So it worked out very well that either students could use to, learn to use the raw data with this, or they could actually use the processed data and use that to plot various things and do some things. So I think even LCO, other than all the multiple archival data which are available, other than that, LCO is also, or any such robotic telescope, is also a very good tool to use, because otherwise, I think students would not have a perception in their mind as to how do we actually get our data, right? How do we plan things? What do we do? Supposing you're looking at variable stars, how do you plan your cadence for your variable stars? And, various other purposes. So I think live observations of this kind is also very good. I think it has to be coupled with the VO data, because otherwise I think the student will be unable to appreciate the data they are handling, right? So, this was COVID and post-COVID, where we conducted a lot of online workshops on using LCO data, and they were well, you can see in the map, they were very well attended by people from all over the world. And we taught them things like plotting the HR diagram with LCO data, doing photometry, because that's basically our area of research. So I do photometry, so that's why. But definitely things can be done on other areas. We were also invited to the University of Sharjah to actually do an offline workshop. This was in December 2022, by the time the pandemic had, subsided and it was fine. So we could actually do it like that. Now, after that also, we've been doing a lot of workshops. We have a little organization called Shrishti. Shrishti basically means the universe in Hindi. And so that's what we call it. And basically we work in photometry and imaging. We've not been doing spectroscopy, but maybe we can extend it on to that. But we were doing various works with, for example, a very simple thing which can be done with LCO as well as with other data sets is, for example, the HR diagram and how is exactly photometry done. So, for example, with the LCO photometry raw data, you can actually show students how to use, for example, the APT tool. There's an aperture tool or various other tools. You could even show them in AstroPi how to do photometry, Dow Fort, for example, or whatever. I think one needs to basically scale it depending upon the audience. If the audience is not, we've been doing it for high school, undergrad, postgrad, various students. So if it is generally students who don't know any coding, so either high school or undergrad students who are not confident with coding, then I think it's very good to use catalogs, directly catalogs, not just the LCO ones, but for example, Gaia catalogs or Kepler catalogs, and you can use TopCat. So TopCat works very well with these catalogs. So a combination of TopCat and Aladdin, for example, can be very well used to describe things. So we'll be presenting that. We have a side program or whatever on the 14th, which is being organized by Patricia, which is basically a day-long workshop on archival data, which will be hands-on session. We have about 30 plus students who are going to be attending that. And we'll be doing various different aspects. Mark's team will handle TopCat, Aladdin, and I will be handling Kepler, Gaia, and TESS. Okay, all these data sets. So we will actually show students how to, it'll be a hands-on thing. So students will actually use Gaia, Kepler, and TESS data to actually plot things and derive things about it. So I'm not doing that today, but that would be done on the 14th. It's a day-long session, and you can find the details of it on the IAU website for the side events. So it's a side event on the 14th, day after tomorrow. So in short, these workshops have been done in various places. I've also been training people at the Arab Astronomy School. What you see on the background is it's in Egypt. This is North Africa. This is the Kotamia telescope. It's a 2-meter telescope, which is run by the Neriage Institute, which is in Egypt. And they have an advanced astronomy school. I went there last year. I'll be going there this year too, at the observatory itself. But again, we use a combination of the data from the telescope as well as archival data. Okay, yeah. So, so this was our last year's plan, which we did in Copperbelt University, like where I told you, where we spent 3 weeks on setting up their astronomy thing. That's Copperbelt University. There's the program over there, you can see it. The science cases which we deal with, we don't have time for it, is exoplanets, Kepler test, star clusters, HR diagram with Gaia, 1D, 2D, galaxy morphology, LCO data, CCD analysis with AstroPi, and various other things with Gaia, because that's what I basically deal with. And so there are various ways, we don't have the time, I'm sorry. But for example, this is with our, with exoplanet data, this is Kepler data, and you can actually use it in TopCat. We use it to actually observe it, fold the functions, actually get the light curve. You can show students how to get the periods, and then from the periods we get the rest. You get the distance to the star and the planet. You can find parameters for the star data, get the size of the planet, temperature of the planet, and various other parameters, the density of the planet. And once you have the mass and the density, you have the density, you have the chemical composition, so you can actually take students, we'll be doing this day after tomorrow, where we take them through this whole trip of finding out details for this thing. Also star clusters, this is using Gaia data. So using Gaia data, you have proper motion data and parallax data for which you can use it to plot the HR diagram. And so there are many more science cases, and do join us on the 14th, and we'll have some special cases with hands-on sessions on using data. Thanks.
Thanks very much, Priya. I mean, there's time for a couple of quick questions now. Anybody has a question for Priya? Okay, there is a question. I think you'll have to stand up and maybe even come here. Oh no, we have a microphone. Okay, there we go. Okay, there is a microphone available for the questions. Yeah, it works.
Thank you. I'm Shanshan Li from NAOC. Yeah, I'm very impressed for all of your work. I wonder how many members in your team, and you can to build a lot of this project. It's all by yourself.
We're 2 people.
Oh, yeah. This it's a lot of work, because I'm very impressed for, like you said, that you can students when learn all of this, and they can go follow the career in maybe different like in software engineer and some others. There is a question about this. Like some students learn from in China, and later then they just go to like software industry, and they lost interest in the astronomy, because it's not a very good income after they learned, and so we kind of teach astronomy to the software engineer, and we teach like coding to astronomers. But later people just go to these different paths. They don't join our team because we want to build our team, and we want people to build the VO and in China and both internationally. I wonder what's the situation in India. Is the students follow your path, or they just go to study astronomy or software engineer? Yeah.
So thanks a lot for the question. It's a very, very important question. And I think I have kind of matured with time. Now I'm quite old. But earlier when I did astronomy outreach or education, it was always so that I'll make everybody an astronomer. That was my aim. But I think I've matured now. I do not think that if the student does not continue with astronomy, it's an indicator of your failure. I think as long as if you can teach the student how to analytically analyze data, I think it's absolutely fine if the student goes. However, a lot of our students who are part, especially the Indian ones, many of them are in touch with us, and a very big chunk of them have gone in for careers in astronomy. But obviously, you know all astronomers, it's very difficult to tell somebody about the beauty of astronomy. If you don't feel it inside you, I can't do anything about it, right? So I think this gives you a short time where you can convey the pleasure, the fun or how good you feel about doing things. And if the student doesn't catch it in that time and decides to move on, I think we should let the student go. Let him or her go, because, we needn't have people who do not feel for it, right? Agreed, you do earn lesser, there's more money in other things. If people want that, fine. I think it's okay. I don't think we should dictate terms on people on how they should live their lives. If they want to go for money, let them do that. We can train them. And I think you always have a small fraction of students who do go on with astronomy. So that's the prize we get.
Okay, so let's thank Priya once again. And the next talk is an online talk by Brad Chenko from NASA Goddard. Can we have can we get Brad on the screen and through the audio?
Good morning, everyone. Can you hear me?
Yes.
Okay, can you see my slides?
Yes.
Okay, well, I will get started then. Thank you so much for this opportunity. My name's Brad Senko. I'm at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And I apologize that I can't be there in person, but I hope you all are enjoying a great meeting and beautiful Cape Town. I'm going to talk today about enabling future breakthroughs in time domain and multi-messenger astronomy. And I'm going to give you the take-home message at the outset here. So time domain and multi-messenger astronomy, the study of time variability in the universe and the study of the universe outside of the electromagnetic spectrum, offers the opportunity to answer some of the most long-standing questions in both fundamental physics and astrophysics. At the same time, this field represents some of the most technically challenging coordinated observations in all of astrophysics. I'll talk about what I mean by that in a few minutes. And so as a result, this is a really great opportunity. Infrastructure, both standards and software, are really critical to fully capitalize on these scientific opportunities, both in the near and in the long-term future. So I'm going to talk through one specific example because I only have 10 minutes or so for this talk. I'm going to talk about gravitational waves, in particular ground-based gravitational wave detectors, and the study of compact object mergers, in particular binary neutron star mergers that these have enabled in the last decade and looking forward. So looking back for a moment to 2017, the discovery of the first binary neutron star merger by the LIGO and Virgo detectors was really a fundamental breakthrough for not just astrophysics, but for physics as well. As a reminder, this was the detection of two merging neutron stars at a distance of only 40 megaparsecs. In the immediate aftermath, in just 2 seconds after the merger itself, gamma ray bursts was detected by the Fermi and Integral satellites. And this kicked off a multi-wavelength campaign to identify and characterize the counterpart across the entire electromagnetic spectrum. UV, optical, near-infrared, X-ray, and radio all played a fundamental part in this. And this discovery enabled an incredibly broad range of science just from one single object. We learned that short gamma ray bursts are powered by binary neutron star mergers. This was a several decade-old question that was answered in the span of just 2 seconds. We learned that binary neutron star mergers generate some, if not most, of the heavy elements in the universe, what we call R process elements, gold, platinum, plutonium. We learned that relativistic jets have an angular structure to them, a narrow core of relativistic material and a wider sheath of slower moving ejecta. We think this is probably a universal property of relativistic jets, though we don't know. Obviously, we want to study more of them. And there were additional constraints on such fundamental physics as the neutron star equation of state through the tidal deformability of these neutron stars, the Hubble constant, nuclear heating. I could give an entire much longer talk just on this topic. But the most exciting part from the gravitational wave network perspective is that this is just the beginning. Ground-based gravitational wave network is undergoing a series of upgrades at the moment. This is improving their sensitivity dramatically. You can see that through these curves here. On the left is showing a simulated population of binary neutron star mergers. On the right, a simulated population of binary black hole mergers. And you can see that as these detectors become more and more sensitive, we're actually starting to probe a larger and larger fraction. At the moment, we can only see sort of the tip of the iceberg, if you will. But with planned next generation ground-based gravitational wave detectors like Cosmic Explorer, we actually could go from a scenario, which I think is kind of amazing, where we detected the first compact object merger in 2015 to within a few decades being able to see every one of these systems in the known universe. I think that's just kind of mind-blowing. So that's an amazing opportunity. What about the challenges? The expected electromagnetic counterparts to these systems span an incredible range of luminosity, wavelength, and timescale. This is a plot that's trying to summarize that here in just one figure. On the shortest timescales of just seconds, we expect if these systems are able to generate relativistic ejecta and it's beamed toward us, we could see a gamma ray burst, short-lived flash of high-energy radiation. On a slightly longer, but timescales of minutes to hours, maybe to just a few days, we expect to see a kilonova from the radioactive isotopes formed in these systems at UV, optical, and infrared wavelengths. And then on longer timescales of week to months, and afterglow where this relativistic ejecta runs into whatever was surrounding this binary neutron star merger and gives rise to synchrotron radiation. And the real challenge here is that you want to look over these range of wavelengths and this range of timescales in very large areas of the sky. Gravitational wave detectors are relatively poor at localizing sources on the sky. Basically, they use triangulation to do that, the different time arrival of the signals to multiple interferometers on the Earth. And you can see some of the first compact object merger localizations here. They span everything from, in the best case, tens of square degrees to, in the worst case, up to thousands, in some case even 10,000 square degrees. So you have to look for this veritable needle in the haystack on very short time scales over very large areas. And here's a practical example from just a few years ago of where this was, really quite challenging. This was from 2019, GW 190425, the second binary neutron star merger that was detected. Unlike the first one, this was localized to something like 5,000 or even, 10,000 square degrees. You can see this plot of the contour of the gravitational wave localization is shown in white. The follow-up that was conducted largely by ground-based observers, you can see the number of times that different areas of the sky were imaged here. The legend on the bottom is showing you that some areas, were imaged 0 times, or there were other areas that were imaged hundreds of times. And you can imagine that, if this were coordinated in a better effort and there were information distributed that allowed people to coordinate in a better effort, instead of people imaging, one area of the sky hundreds of times, maybe we could do a more effective job of covering this entire localization and increase the likelihood of actually finding the counterpart. So that leads to the opportunity, the building of tools, the developing of standards to allow people to conduct these coordinated observations on short timescales and over large areas of the sky. I'm just going to talk about a couple of illustrative examples for this, and then maybe in the discussion, we can talk about a bit more about what is needed going forward. But the one that I'm most familiar with, the General Coordinates Network, or the GCN. For those of you who have been in the field for a while, you may have known this by its old name, the Gamma Ray Burst Coordinates Network. It's been updated and modernized and improved over the last few years, led by a group of folks here at NASA, in particular, Judy Recusson and Leo Singer. And the idea here, this was coming out of the gamma ray burst community, but was to enable a way for people to communicate in an entirely automated manner the discovery and to trigger follow-up of fast timescale sources. So you can see kind of the idea here. You have some astronomical transient. It's observed by a network of facilities in space and on the ground. The GCN acts as a hub and a standard system to allow people to distribute information about that source, to trigger robotic follow-up or even non-robotic follow-up, and to share information so that we can characterize this source over the very short time scale in which it is accessible. Another example of that is the treasure map. You can see the URL here. This came out directly of this challenge that I was showing you before of covering these large gravitational wave areas. It's a site that allows you to not only upload areas on the sky where you have observed with your telescope, but areas on the sky where you are planning to observe, so that we can do a better job of coordinating this large area follow-up on the sky. You can see here a recent example from 2024, just back in April. This was a pretty well localized source on the sky, but still the area was of order 100 square degrees, and all the different colors are showing different facilities that were doing follow-up on this area. Allowing observers to know where other people were looking so they could plan how they wanted to observe with their telescopes. And last, I just wanted to talk about one particular VO standard, the OBS-LOC-TAP standard. This was designed to allow observatories to report both where they have looked in the past and where they are planning to look in this sort of very generalized network. This has been extremely useful, and in particular, a lot of the space-based observatories have been adopting this quite widely. I think it's been, people have built, a bunch of different tools over this. This is just one example that allows people to know, okay, here's where on the sky different observatories have looked, or are planning to look. And so they can, base their precious resources with this kind of full suite of knowledge. Okay, so I'm going to wrap up, just kind of repeat, what I started with. Sorry, I meant to copy the wrong slide there. The take-home messages here, time domain multi-messenger astronomy, right? Really getting at some of the most long-standing questions in astrophysics. Very technically challenging. Just one example here, covering large areas in short time scales. But building this infrastructure is really critical to enable us to capitalize on this really exciting opportunity. So I will stop there and gladly take any questions that people may have.
Thanks very much, Brad. So we have time to take one question for Brad. Is there anyone in the room? Manon, I have the microphone here.
Hey, thank you for the talk. I was wondering where we can find the OBS-LOC archives.
So different observatories maintain them in slightly different ways. I know the space-based ones are working on putting together a coordinated one, but for example, in Swift, we have ours. It's linked on the Swift website, and if you need help finding it, by all means, reach out to me and with an email, and I'm happy to help dig up some of the other ones as well.
Should move on to the next talk. So I invite Russ Taylor to the podium for his talk on big data and.
Hello, can you hear me? Okay, we'll get our.
And if we could have the slides for Russ Taylor, perfect. Thank you.
Thank you. Hello, test. Okay. So, hi there. I'm Russ Taylor. I'm part of the South African Inter-University Institute for Data Intensive Astronomy, which you can see on this slide is a collaborative institute between 3 universities in South Africa, the University of Cape Town, the University of the Western Cape, and the University of Pretoria. And that institute was set up in 2014 to address the issues of, at that time, the emerging problem of big data in Africa. We're now, of course, in the thick of the big data in Africa, by building multidisciplinary teams to build solutions and software and expertise. So I'm going to tell you a bit about the journey and highlight the relevance to the themes of this session, which is open science engagement and collaboration. So the journey began in 2018 with the construction of the Meerkat, the completion of Meerkat in South Africa. Meerkat is the precursor to the SK Mid facility, which will be finished towards the end of this decade, and Meerkat will be merged into that facility. This plot shows a growth in the data in radio astronomy worldwide. It's a log linear plot, so a straight line on here is the Moore's law exponential growth in data. And you see up until about 2018, there was a growth around the world, doubling time of about 2 years in the size of data that's astronomers have to deal with in radio astronomy. But here in South Africa, the red line shows the South African growth, or the African growth, which is now a much faster doubling time of about 9 months. And we're now currently in the Meerkat era in the petabyte scale problem in data and radio astronomy. At the same time, the way we're doing astronomy is changing with these new facilities, these new large, unique global facilities. We no longer are driven largely by individual researchers observing and taking their data home and processing it and writing papers. We're driven by large global collaborations that are doing key science projects on large facilities that have a large amount of time on the telescope, producing very large data sets, and being executed by teams that are distributed all over the world. And that's a new way, and it's driving new technologies to help facilitate that kind of research. So the Meerkat telescope is foreshadowing that approach to astronomy. It's basically operating in the same way that the SK will operate. It's allocating about 60 to 70% of its time to large projects. Each one typically 1,000 or more hours of time on the telescope, producing very large data sets, addressing key science on the pathway to the SKA, and producing and being executed by large global teams. So we're now in this process. So how do you deal with this problem? Well, there was a very interesting book written by Al Gore in 2013, called the Future 6 Drivers of Global Change. It's a very interesting book. I highly recommend that you read it. One of those drivers, of course, is the digital revolution that we're going through in technologies for digital connection. And he talked about the emergence of a planet-wide communication grid connecting researchers and people all over the world. And that technology, sometimes called the Fourth Industrial Revolution technology, is changing the way that we can do science. In the old days, we had a hierarchical approach to dealing with things. We had a top-down, chain-driven reporting infrastructure to deal with problems. This new technology is driving the ability to have a collaborative commons, where we take diverse talent and expertise from all over the world, bring it to bear on problems in a collaborative way. And that's the revolution that we want to tap into. So one of these technologies is cloud. And IDEA, in collaboration with several partners in South Africa, has constructed a cloud computing system for data-intensive research called ILIFU, which is the Xhosa word for cloud. This is built upon a petascale computing system that's hosted at the University of Cape Town and operated and administered by IDEA. It was designed by Professor Rob Simmons at the University of Cape Town, as both in terms of the infrastructure and the cloud software and platforms that operate it. It's a petascale system. Right, so ILIFU is hosts projects, right? And this is a plot showing the range of projects. The vertical axis is the number of researchers involved in that project, which pretty much scales with the amount of data that project is dealing with. And the blue are the astronomy. We also serve bioinformatics research in South Africa. And you see the big red thing on your left is a large genomics project, a Pan-African genomics project that is being served by the ULIFU system. But all the blue stuff is the astronomy projects, and the big ones on your left are the large survey projects with Meerkat, and they get smaller as we got out into the open time PI-driven projects. There's about 80 or 90 projects currently hosted on ULIFU. And about 500 and some astronomy users. And the pie diagram on your right shows the distribution of users by country and institute. The big blue part, which is about half the pie, is South African researchers. The rest is international researchers from mostly Europe and North America. And it highlights the fact that we are serving a large collaborative community of research from all over the world, using ULIFU to do collaborative research on big data and astronomy. We're also, about half of those users are graduate students. So we're training a large cohort of postdocs and graduate students in big data and data science and astronomy, and working with the data, which is where the power is in this data-intensive world. Okay, so this is the way it works. On the left-hand side here is all of the stuff that's hidden from the user. That's the cloud technology, which takes advantage of Singularity containers, OpenStack cloud software, virtualization of networks and machines, and Slurm distributed task management system, and various bits of software that we put on top of that. The users come in from the right, mostly through web interfaces. Right? So the idea is that this system allows you to work with big data on your laptop anywhere in the world as if that big data were on your laptop. And all the services and platforms you use to work with the data are web interfaces. You access those interfaces using a gateway. And here you see an example of the primary services that we provide. If you click on the Jupyter one, you get a Jupyter laboratory instance. And these Jupyter lab environments are shared by a project. So all the resources, all the notebooks and the data for that project are available through this Jupyter interface. And so we can collaborate as project teams from around the world by sharing notebooks and co-developing notebooks. And it also allows us to have a reproducible track for our projects. So the Jupyter notebooks are then part of the publication of the scientific results and allow users to reproduce your results. If you click on the Carta one, our Carta visualization tool comes up. Carta is a project led by IDEA with collaboration with NRAO in the States, AGA in Taiwan, and the University of Alberta in Canada. And this is a cloud-based visualization system which allows you to visualize the large data sets resident on the cloud. What you're seeing there, it looks like it's a single image, but actually that's a hypercube. That's a single plane of a hypercube. That's about 1 terabyte in size. And all the analytics around it are showing you properties of that hypercube. We have built into this system a workspace concept and the ability for people that are all in the same project to collaborate in data, visual analytics of data, and to share views and resources. And we also have, of course, access to the IVO resources, so we can bring in data from the IVOA to overlay on images to do analytics. One important aspect for reproducibility is the fact that because everything is container or kernel driven in terms of being deployed on the cloud, we have a repository of containers, which is also a key aspect of reproducible science, because the container contains all of the software and environments that you use to execute your analytics on the data, and it also becomes part of the chain of reproducibility of your science. And you see that we have quite a large repository of containers. Every container that's ever deployed on ULIFU is preserved in the repository, So if you used a specific version of some container for your research, it's available and will be there historically. And here's just a list of all of the containers that include the NREL CASA, the CASA systems. And this diagram shows the processing pipeline for where we can deploy those containers to process your data. And what's important about this diagram is it empowers the end users to calibrate and image their data the way they want to. It's all module driven, primarily by Python modules, and you can plug in your own. And all the deployment of that on the petascale computing system and the access to data is handled by the back end. You don't have to worry about it. You just put in your scripts and process it. So it allows us to tap into this collaborative commons of people working on ways to calibrate and image their data and process them without having to worry about all the stuff on the back end that allows you to access the data and the compute. And it's producing things like this, which is one of the large survey projects on Meerkat is MIGHTY, which is the deep imaging of large areas of the sky. And we're on our path to the billion radio source universe, which is coming up in about 3 or 4 years. Okay, so the other aspect of this session is engagement. We have a team and idea specifically devoted to development and outreach, to take the work that we've been doing and try to maximize the benefit to society at large from both the technologies and the access. And you may have seen some of these smiling faces at the IDEA booth over here over the course of the meeting. I want to highlight one box in this outreach program, which is the hackathons. We have used the cloud technology to go around Africa and to run these things called hackathons, which are multi-day events where students from African communities get together and work are trained on data science and work on big data projects by interfacing to the ILIFU system. So here in the upper right, for instance, this is Madagascar. It's a little place at the northern end of Madagascar where we brought some students from all over Africa in collaboration with Dara Big Data. And you see that they have laptops connected to the Wi-Fi at the location, and they're accessing the ILIFU cloud and the resources on the ILIFU cloud. We have special platforms for hackathons. I'm working on big data problems from this remote place in northern Madagascar. We've also done it in Botswana. We've done it all over the place. And we're now working with a new set of partners. You see the long list at the bottom there on a project called Hack for Dev, which is using Hack to address the development goals of the IAU. We're doing a training for hackathons where we bring people in and train them how to do hackathons so we can build a network of communities around the world in the hackathon community. And just next year, we're going to be hosting 15 hackathons all over the world using the ILIFU cloud system. So it's a very powerful outreach and engagement program to reach traditionally disadvantaged locations where they don't have access to these kind of facilities. Just end up by pointing out that we actually won an award this year, a national award in South Africa by the NTS, the National Science and Technology Forum. It's called the Science Oscars in South Africa. And we won for the special theme of Fourth Industrial Revolution in South Africa for our cutting edge infrastructure and management, which facilitates global collaboration in astronomy and empowering researchers to analyze complex science and engineering and technology data with unprecedented efficiency. So we're very proud of this award.
Let's thank Russ. Thanks very much, Russ. It's time for a question or two. Chenzu?
Russ, ILIFU is a very successful science platform. So is it free for registered users, or you have to pay for the platform?
No, it's free. The platform was funded by a combination of funds from IDEA and from the South African CSIR. And so the facility was built with public funds, and it is provided free. The only proviso is that for a project to be accepted to run on ILIFU, it has to be led by a South African team.
Yeah, and so I feel the science platforms are facing a common challenge. That means who will pay for the backend infrastructure? And otherwise, if we cannot find a solution, so all the science platforms will be stopped at technical demonstrations, and it will be very hard to put it into real operation. So do you have some ideas?
You're very correct, Chenzu, that scaling this up for the coming challenge in the next half decade is going to be a challenge because we have to increase by about a factor of 10. And I think within the SGA context, we probably can solve this with the Science Regional Center concept, which will be funded by member countries of the SGA consortium. And if we do that right, we can serve more than just radio astronomy, like ALIFU serves bioinformatics as well. So we can maybe leverage the SGA investment to benefit a broader scope of science. But I think more generally, it's going to be a big challenge here.
Okay, let's thank Russ again, and congratulations on the prize. The next talk is another online talk by Bruce Berryman, who was originally attending to come here, and Bruce has provided us with a recorded presentation, but he is available afterwards on the Zoom for questions. So if I could ask for the next presentation to be shown, the video, please.
Now, the three items are all related. The development of a fair framework developed as part of a worldwide collaboration among archives and data centers will lead to a sustainable open architecture that will lead to exciting new multi-data set, multi-wavelength science. Implementing IVOA standards goes a long way towards implementing FAIR standards. I recommend a talk on this topic by Simon O'Toole, which was made at A-30 in 2021. You can watch it on YouTube. You can also read the paper in the conference proceedings. The next two charts will show you where we're compliant. There are a number of principles that are really out of scope for the BO. They're best left to the service provider and others that are really incomplete. For instance, 1.2 metadata associated with a detailed provenance. And you can see how this compliance comes about if you look at a schematic of the infrastructure of the architecture of the VO that's been built up over many years. The four pillars of FAIR principles each have an analog in the IVOA architecture. A registry, which is sort of a yellow pages for astronomy, enables finding and discovery of data. Getting is the equivalent of accessibility through the protocols. Sharing is the equivalent of interoperability among different data sets, different archives. And finally, using at the top is the equivalent of interoperability. All right, so I mentioned that IVOA standards do go a long way towards compliance. How do individual data sets stack up in all of this? So here's a list of Australian data centers from Simon's talk. Simon's an Aussie, that's why it emphasizes the Australian data sets. It's a bit out of date, but it is nevertheless instructive. You can see that a good number are compliant. The red boxes indicate where they're partial compliant. Now, FAIR is actually a continuum. It's not a binary yes or no. So there's a wide spectrum of compliance with FAIR principles, and you see that here. So wonderful. All astronomers have to do is implement VO protocols. We're done. We can all sing Kumbaya around the campfire. No, there is a long way to go yet. And the work I'm going to describe in the following slides, this represents a snapshot of the work that we're starting to do and is now underway. And note that what I'm about to describe is actually true of all disciplines to one degree or another. And first of all, there's no validation that we do of these principles. There are efforts underway to develop a validator. Our colleagues in France are studying, for example, the applicability to astronomy of a validator originally developed by the French bioinformatics community. Another group in France is actually studying the fairness of the virtual atomic and molecular data center. So this is work in progress right now, and other fields, of course, are also developing and addressing this topic of validation. Now, another concern lies in persistent identifiers, a long-lasting reference to data. But there's more to identifiers than just the reference. They need to be unique, obviously, and persistent, but they also have to be machine resolvable and processable, and that means they have to have an associated metadata schema. Now, the US government definition I put on the right-hand side takes account of that requirement to have metadata schema. It's not necessarily a better or more rigorous definition than any other. It's simply the one I'm familiar with. All agencies have a definition that is broadly similar to this. Now, metadata is right up the IVOA's alley. And we're working on our schema for astronomy because of parallels of DOI metadata and registry metadata. And you can see that here. That's a summary of metadata from the registry on the left and DOI metadata on the right. I wouldn't try reading all that dense information, but you can see from the labeling that there's a direct correlation between the various classes of metadata. Fairness is a worldwide effort. Want to work with and learn from other disciplines. Deborah Elmer-Green asked me to be the IAU representative to the Co-Data Committee on FAIR Standards. I attended a VideoCon in June that was attended by representatives of many disciplines. A lot of common frustrations were expressed by these organizations and disciplines. What exactly do all these FAIR principles really mean? Is there tooling available? How is FAIR compliance going to be funded? So, this is a worldwide issue, which we all want to work on. So I think we're going to have to do it by working together on these community standards. Now, one example is Onto Portal, which aims to develop a framework for ontology management. Now, a number of disciplines have already signed on to this and are working within it already. And you can see a list of those in the chart on the right-hand side, which is taken from the Onto Portal website. Astronomy is working on a prototype of this with our colleagues at the observatory in Paris, in France. All IVA vocabularies have been imported, although not always successfully. And the scope of the work is pretty broad. We're including astronomy, planetary science, heliophysics, particle physics, and atomic and molecular data. So with the next, well, obviously we want to continue to promote FAIR principles in the IVA in astronomy, continue with the FAIR development work that I've summarized in the previous few slides, definitely engage with other communities, share war stories and best practices, share and adapt tooling and validators. A number of disciplines have in fact already developed validators that we can maybe take advantage of. I showed one example earlier. In the end, of course, we hope that all of this will lead to exciting science that we can't do now. Come back in 2 years.
473 scientists signing the pact.
Thank you very much.
Okay? So it was a large proposal with a lot of support from the community that had the sun.
A little bit of extra background noise just in a moment. Okay, it seems to be fine. Bruce, are you online to answer questions?
Yes, I am.
Thank you. Okay, so Bruce is online to answer questions. So please, is there a question in the room? Okay, so I don't see a question in the room. Bruce, perhaps I ask a quick one myself. I mean, how do you see the astronomy interoperability that we have through IVOA connecting to the interoperability at a different level for the like the on portal that you just mentioned? Do you see that as something being more political or more practical?
I think to some extent it's politically driven. Certainly in the US, the Space Mission Directory at NASA, who provide me with my funding at IPAC, have essentially directed us to do this kind of work. So yes, there's a political aspect, but ultimately, I think the political aspect, I hope, will give way to enabling new science. There's no point in doing it unless the science gets done, if it's improved. Will this happen? Honestly, I don't know yet. I would say we keep at it and keep that as the goal and make it happen. But it might take quite a few years, I think, to get there. I think one of the problems that a lot of people, a lot of disciplines have noted, this was really apparent when I was on the CoData Telecon, is a lack of funds to do this. I mean, people have been directed by various agencies, but without accompanying funds to make it happen.
Okay, thanks very much for your answer. Let's everybody thank Bruce again. And now I will ask for the last slides. In fact, it's the talk by me, so I will go to the podium. Someone is supposed to give me a 3-minute break. Okay. Okay. So it is my pleasure to also give a presentation in this session. Well, I had my slides a moment ago. Now, here we go. Here we go. So I'm Mark Allen, and I'm presenting work which has really been contributed a lot to by my colleagues at the CDS, which is the French Astronomical Data Center in Strasbourg, called CDS, and we're hosted by the Observatory of Strasbourg at the University of Strasbourg. And I'd like to mention also a lot of the work we do towards the international level standardization at the IVOA. So at this meeting, I wanted to come and say a few things about visualization of very large data sets. Not because we have all of the answers, but I think we have some of the parts of them. And in fact, what I see in the community is different expertise coming together in the context, for example, of the SKA, attacking and looking at different aspects of how we're actually going to look at the very large data that is coming. So we can see petabyte scale data coming from experiments and facilities like the SKA, but also space missions like Euclid, and also the large, the LSST Vera Rubin Observatory. And there's many aspects to visualization. One can be that you want to explore the data on all of its scales. You want to be able to sort of stand back and see it all in some way, because that gives you some sort of idea of its scope, of its coverage, of its depth. So you might want to look at the full sky of your data. But then, of course, we're astrophysicists and we need to have our hands on the real measurements. So those individual pixels are also extremely important to us. So how do we have this full-scale view, but then also have the ability to drill down to the individual pixels? Of course, our use cases will include very detailed analyses of multidimensional data, extraction of data from very large data sets, and we also want to be able to combine them, because we're in an era now of not just multi-wavelength astronomy, where we combine data from different telescopes across the electromagnetic spectrum, but also from different messengers, from particle showers or from gravitational waves. So there is a whole slew of data that we want to be able to access and visualize in some kind of way. So what I want to concentrate on in this talk is that visualization one needs for data discovery, to get the overview and the quick look. And I do that because we do actually have already some success in distributing some of that very large data from all-sky surveys in various systems. And so what I'm showing you on the screen now are all-sky views of different types of surveys that have been made available through virtual observatory standards and enable a view of that data that is fairly global. So we've gone through a few different wavelengths there. That's the pan-stars, that's an unwise infrared image. And now we're using some of the aspects of visualizing that data in a hierarchical sort of way, meaning that you can get the large scale view, but then if you zoom in, the system that I'm talking about here accesses higher and higher resolution versions of that data, and it sort of streams to you in a live way the pixels that you need on the screen to see that view at this moment, because it's certainly not possible to download these data sets in a way that allows you to play with them like this. So here we're zooming into M51, having a look at it in different wavelengths from different telescopes, and you can see the instrumental characteristics of the data are really different. Now we start to see some higher resolution images of M51 in radio, and again in the optical, the pan-stars view of that galaxy. And what's just about to happen is another zoom in, I think. So in the X-ray, all of these data have been put online through virtual observatory protocols, and we have tools to access them and combine them in this manner. So I'm going to move on. Okay, so what makes that work behind? It's some of the IVOA standards, in particular ones that are called HIPS and MOC. So they're funny kinds of names, but the HIPS is a hierarchical progressive survey that's based on the heel-pix tessellation of the sphere. So what you do is you take the sphere And instead of trying to address all of the points on the sphere with our spherical coordinates of right ascension and declination, we basically split it up into a hierarchical system that allows us to index the sky at different resolution levels, we call orders, and to sort of express the data in this multi-resolution way. So there's various aspects of HEALPIX which are nice. It was developed by the cosmic microwave background community and built on, of course, 18th century mathematics. There are no singularities at the pole, and the pixels are of equal area. That's what the EA is in HEALPIX. And there's an IVOA standard that's been described since 2017 and papers going back to 2015. And so what it means is splitting up the sky like this, and it's equal area, it's isolatitude, there's a nested indexing scheme. And what's really nice about this system, going way back to the cosmic microwave background efforts, is that there are open source software libraries for dealing with this. And Bruce didn't want to show you all the details of an IVOA standard, and against some people's better judgment, I like to sort of dive deep on this part of the IVOA standard, in that it's basically a tabulation of the indexing of in the HEALPIX system. And the main point I like to make there is that in this same system, you can describe a fairly low resolution survey on the sky, like the W map, or even the Planck data, which has resolution of like 7 arc minutes in the case of W map, or Planck at 3 or 4 arc minutes. But in this same system, you can describe the 25 milliarc second ACS or pixel from the Hubble Space Telescope. And we have a system of pixels and tiles that is described in this standard, and it's one of the easier standards to use of the IVOA, in that if you look at the examples, you can kind of follow the example, put your data online, and it makes it available in this sort of way. And this standard turns out to be a kind of useful container for any information that you can put on the sky. So the example I showed you was of images, but you can also use it for catalogs, where you have a hierarchical view of a catalog. And these days, a catalog can be up to 2 billion sources, and we can expect the Euclid release to be of tens of billions of sources, and of course the large telescopes will come even further. As an aside, some of these systems also work well for planetary surfaces, for density maps, and you can see the Gaia map on the bottom right there. There are some 21 nodes that provide this data these days around the world, and you can see it on the map there. We call those HIPS nodes, and the machine behind you can call a HIPS server. So these are places that have adopted the standard and made various data available, and you can even clone different data sets to do that. In the registry, there are some 13 or 1400 HIPS data sets already available, and it adds up to about 700 terabytes of data that's there now. And if you think about that in terms of pixels, you're talking about 10 to the 14 pixels. HIPS in use, you can access it, and there are many people who are actually doing this, because the systems like the ESA Sky or the ESO Science Archive, they use this system behind in their archive system, and you can see some of those. One of the clients that comes from the CDS is called Aladdin, and it allows you to combine data in that system with catalogs, and to overlay and to do your science in a fairly full-featured tool. There is an application called Aladdin Light, and I've zoomed in here on the beautiful meerkat map from the center of the galaxy, which has been put into this format. So there are quite a number of clients. It sort of has a life of its own now. There's the ones that come from the CDS, but also the Worldwide Telescope, the Stellarium desktop, the Firefly system used by LSST, various planetarium software like Digistar and RSA Cosmos, and a few others. So here's just an example of that, showing ESA Sky and the ESO Science Archive, which have embedded Aladdin Light as part of their archive systems that allows you to make access to all of those data that are available. And I'd like to highlight that we are integrating that as a test into the prototype SRC Net Science Gateway. And so you can see here the use of that system where you're looking at different data sets that in a prototype that would show you, using the IVOA standards, the part of the sky that that data takes on. And so this is a part of visualization for data discovery. Our idea is that that you can use that system to kind of browse the data to get a quick look like you might be getting here, and using other VO standards or even integrated into the portal itself, it can provide the kind of launch point for launching into Carter or launching into another system which does a server-side visualization. And part of the reason we think that that's a good idea is that, Aladdin Light and the system you've seen is usable by tens of thousands of users at a time. And we expect that some of the more resource, more of the applications that need higher computational resources that may not be able to offer to tens of thousands of people at a time, but maybe hundreds or tens, that is a way of enabling people to get the overview, and then when they need to go deeper, they can use this type of thing to then launch into a different type of service. So that's the idea that we have a visualization for data discovery. And this is kind of what I just said now. This is a scalable system in that all you have to do is put the data in the right format on an HTTP server. It's able to use to handle tens of thousands of users at the same time. We tested that actually when the JWST made their release of some first images and they were put into this system. We could really see the very strong peak because this data was linked to by all different sorts of news outlets, and people in the general public were accessing the different systems. So tens of thousands of users is really possible. There are a few trade-offs, of course. When you do HIPS, you have to recompute or reproject your data onto a HEALPIX gridding. So it is a regridding of the data, and care needs to be taken when you're doing that for scientific data. And like I say, it's meant to be complementary to the server-side remote visualization systems that are coming about. And with that, for free, you also get a kind of hierarchical way of manipulating sky regions. The complementary standard to the HIPS is called the multi-order coverage map, which allows you to deal with areas of the sky and to ask questions like, does this survey overlap that one? And in fact, you can do that with thousands of surveys at the same time with the various libraries. And there are prototypes and libraries out there now that you can also say, was this, do these catalogs or do these data overlap in space, but also in time? So with that, as a bit of a teaser, I'll move on to my summary. Hierarchical systems, which this is, enable scalable visualization. We've seen it's working quite well for images. There are challenges for cubes, of course. We are working on that in coordination with the work for SKA, and we foresee a future where server-side visualization and this pre-computed hierarchical visualization can work together. And with that, thanks for your attention, and thanks for coming to this event in the hall here. Thank you very much.
Thanks, Mark, for such a pretty enlightening talk. I just wanted to talk about your last point about the interface to server-side analytics tools. We are in the next version of Carta implementing a HIPS integration so that we can access the HIPS repositories and expand our analytics to include multi-wavelength data sets using between HIPS and the SKA. And I really look forward to exploring that aspect going forward in the future with you.
Thanks very much, Russ. Yeah, I mean, I think the place here is getting the different groups that have the really deep expertise in different areas of visualization and talking to each other about it.
Hello, thank you for the talk. I wanted to know if you could explain a bit more how do you use HIPS with data cubes?
In fact, there's already an implementation of HIPS with data cubes where essentially you have just side by side on your disk, you will have the hierarchy of each plane actually. So it's a way to do it, but it's a bit slow because it doesn't actually the format that we have at the moment doesn't recognize the other dimension of the cube. The tool can understand that one plane comes after the other. So we're toying with different ways of dealing with cubes. One of the things that's been explored and that seems to be useful for a certain type of cube is to actually generate the HIPS on the fly. And other experiments that allow you to make the sort of cut through the cube so that you can sort of pull out the spectrum and put that in there. So we don't really have a magic solution for that yet, but it's one thing that we're really investigating. And it's going to be a trade-off, you know, as to how quickly a user will want to flip through the planes of a cube or how much averaging of different planes of a cube would be acceptable. And we're playing with that now, and we hope that it works out well. Yeah. Okay, so I think I would like, we are at the end of our time, but I would still like to give 5 minutes chance of having the speakers from the session at a panel, although I noticed that Priya is not here. So maybe I ask Russ to just join me at the podium here. And am I missing somebody else? Maybe we'll both sit down at the... Okay, so I think we have Bruce and Brad still online. So let's let me just put a timer on as well. From my point of view, we saw a few different aspects of engagement. Priya has been extremely successful at running schools around the world online and here this week. I wonder if you can tell us more about your hackathons, actually.
Yes, I can. We've been running them since about 2017. Starting out, that one picture I showed in Madagascar was our first one outside of South Africa. And they've just grown and blossomed. I think we've reached a couple of thousand young researchers or young people around Africa using this technique. Moving forward, we are taking it to the next level, building a network of groups interested in this kind of activity and doing them worldwide. The way they work is we have a set of data science projects that we bring to the hackathon, and they're not all in radio astronomy. We have bioinformatics and earth imaging science projects. And we break up into teams, and we provide them access to the resources on Alifu. And we have tutors, and people learn how to do data science projects.
Thanks for that. I wonder if Bradchenko is still online, because I would like to ask if there is sort of community engagement events that happen for the GCN, for example. If someone is new to the time domain field, is there a way of engaging with that? Brad, are you still online?
I'm still here. Can you hear me?
Yes, we can.
Great. So the GCN in particular, when it rolled out what it's calling, its new sort of modernized interface, it did a series of webinars. I'm almost certain that those are recorded and placed on their website. I will double check actually right now while we're doing this panel. But those would be a great place to start. There's also really good documentation online. There are example software, Python, Jupyter notebooks for people who want to get their hands dirty with this kind of work. But I think, having more of these going forward and updating them when new capabilities are enrolled is certainly a good idea and something that I'm sure the team is planning as well.
I'll just add that if you want to reach sort of places where people are challenged in terms of access to resources for these kind of things, the cloud technology is really key. And happy to have a chat with you about how to deploy cloud infrastructure for this purpose. We actually ran a hackathon last Sunday here at the IAU GA.
It makes me wonder about where we are. Can we have some place where we can go to find the different types of training materials and things? Maybe it's a challenge to us to have a place where that can be. There are various GitHub repositories, and people are talking about even sharing. You can have containers or the notebooks or the tutorials in different formats.
Yeah, in fact, we have set that up at the Hack for Dev collaboration. We've set up a website, hackfordev.org, which I encourage you to check out, which has resources for hackathons and instructions.
I think I'd like to open up to into the audience to ask questions.
Okay. Actually, you asked what I want to ask. It's like we send two students to participate at hackathon last year here in South Africa. Actually, we held some hackathon in China, but we were very pleased to take what happens in South Africa to China, and maybe we can use the data you provide online to have some hackathons in China. I wonder, is all this data been open to use? And sometimes we cooperate with some industries like AliCloud, and if this data can be used in this kind of events, is there any regulations or is restricted?
All of the data that we use for hackathons is public domain and can be used anywhere. I think sometimes across national boundaries there are different regulations in terms of access to data, so we need to be very careful that we use data that's open and accessible.
Another question, please.
Maybe a comment. From my experience, what we have learned is it's important to go back to the same set of people over and over again, rather than having one workshop or so. But we find students who are interested, and we include them into activity consistently over a long period of time, and then find mentors for them in the relative areas they're interested in. And that has led to a lot of good work. People have gone into serious research and they have published papers too. So it's important that we have a consistent interaction with the same set of people.
That's a very important point. We learned that lesson. When we started doing the hackathons in 2017, they were one-off things and people left and we didn't maintain contact. But now we're working on building a network of researchers or people that have been involved in hackathons or interested in hackathons, so we can grow this into sort of a Pan-African and global initiative.
Okay, there's another question at the back.
No, just to reinforce that, we also have a program where we have a sort of hierarchical system of mentors. Teachers then pass on the knowledge to a whole platform of others who then fan it down. And then those people become mentors of the next generation. And so this is just one of the mechanisms where we're trying to address exactly the problem that you raised there. Thank you.
Yeah, that's right. Thanks. By the way, that was Ketchel, our project manager from IDEA. And what she was talking about is what we call a cascade outreach model where we have mentors. Can I veer off in a different direction? I think one of the challenges that became apparent in the talks was the Open Science Challenge. We haven't really built the tools and mechanisms and interfaces to address the open science issues. We have bits and pieces scattered around that different people are working on, but I think we do need to, as a community, rise to the challenge of talking to each other about how we bring all these bits and pieces together to build something that can evolve into a sustainable open science approach for big data.
Thanks very much for that. I guess I think part of the answer to that is the standardization and what we do at the IVOA. IVOA has 2 interoperability meetings per year. The next one will be connected with the ADAS meeting in Malta, and I'm expecting the one in May of 2025 to be in College Park in Maryland. Of course, it's difficult to, like we've just done here, to travel all of the way around the world. So it is challenging to do that. There is an online community as well, but I think that we can perhaps here at this event make new connections and just reinforce that idea that there are places that one can go. And I'm really interested to hear about the other communities that may not be as well, know very well about IVOA and to get them involved and to also just understand what other types of protocols and things people need to make those things work. Perhaps at this moment, I can ask if there's any of the other online panel members who would like to say something. I think we've run 10 minutes over because of the technical glitch, but I think we can go just a few minutes more if Brad or if Bruce would like to contribute to the discussion. If not, that's okay. We can follow on now that we have the connections. And so with that, I think, unless there's some other questions in the audience. One more, please.
Hey, Russ. So I wanted to find out how can other observatories that are not necessarily part of what you guys do join? For example, I work at Hartarayo, and we've got lots of data which we think would be valuable for your hackathons. So how do we get in touch and see where we can contribute as an observatory in the country?
As I noted, ILIFU serves researchers through projects. So if there's a project that you wish to pursue that we could make use of ILIFU resources, then just contact us and we'll talk about getting that set up and meeting your requirements. If Hartebijsthoek wants to actually formally be part of ILIFU and contribute to the development aspects of what we're doing, we are open to new partners in the IDEA project.
Okay, and with that, I think that I'd like to thank everybody for coming, thank all of the speakers. And please don't hesitate to get in contact with anyone you've seen today and to make the engagements that are necessary for us to go forward with these types of things. So thanks very much again.
O mepere unu. Ngwazikwa ka last one ka m mebiri. O mepego unu nọ na onweghị ihe mma na-eme ebe a. O mepego. O mepego. Ngwa thank you. Is open, o mepego.
That's on. Yeah. Good. So I guess, yeah, now hoping you can hear me. So welcome to our Unconference session on the future of scholarly communication. We should talk. And I hope that this session will be highly interactive, so we have a microphone here that I will give to you. Feel encouraged to be part of the debate. Let me briefly introduce myself. My name is Martin Dominic. I'm an astronomer at the University of St. Andrews in Scotland. I've done some work on this topic over the last decade or so, mainly with the Global Young Academy and the wider global network of young academies. I very deliberately used the term communication rather than publishing, because that acknowledges the fact that scholarly communication is a process, not a one-off event. Moreover, we should not confuse means with goals. Communication is an integral part of science, and building a trustworthy record of science involves critical scrutiny. Over recent history, astronomers tended to be no strangers to embracing new technologies and adapting working procedures. The first Central Bureau of Astronomical Telegrams was established in the 1880s. We share articles on archive for 3 decades, and the largest part of the literature is findable on ADS, now even with full text search. Astronomers practiced open science long before policymakers started even talking about it. However, scientific journals appear to be an anachronism, a 17th century solution based on a 15th century invention, namely the printing press. Are these still fit for purpose in the era of the internet? How would a platform for scholarly discourse and global community engagement look like based on 21st century technology and recognizing the society of the 21st century? Let us also recall Article 27.1 of the Universal Declaration of Human Rights. Everyone has the right freely to participate in the cultural life of the community, to enjoy the arts, and to share in the scientific advancement and its benefits. On Friday, Hotzo Mokele made a strong point that the way forward should not be to confer high prestige to science being presented so that as few people as even possible can understand it. Wikipedia is an amazing example of a global community effort. It is mostly self-organizing and provides a high degree of transparency. Alongside the article page, there's a talk page, open for discussion, questioning the veracity of statements or calling for supportive evidence. It is not perfect, but what can we learn from it? What actually stops us from doing things in a way that would actually make perfect sense? And I would like to hear your thoughts on that. So, who wants to say something? Who wants the microphone?
So I think it was interesting in this morning's plenary, part of this topic was discussed, and Professor Schmidt mentioned that the infrastructure that we have through archive is something that we could potentially build on in astronomy to create a more open publication environment. I'm quite interested to think about how peer review would work in something like that.
Anyone with further thoughts on that? So, we have some nice infrastructure. Astronomers solved the problem of open access 30 years ago. Now we're going backwards. We see astronomy journals being transferred into an APC model, which really is not open access, because it might be accessible to readers, but it's no longer accessible to many authors. So that doesn't work. So where's the obstacle? So would you see the chance that we could put a peer review system on top of arXiv? Would that solve the problem, or do you see any other parts to the puzzle that need to be addressed?
This is like a dialogue of two people in a public space. So I think one of the things that has to be addressed is the kind of weight of publishing in established journals. There's a kind of a reputational, there's something about, the importance of reputation that comes with being able to publish your results in, a well-known journal. And I think if you look at smaller societies, they do host their own journals, yet even with indexing and probably even peer review, often those kinds of publications don't get well cited and don't make it into kind of the mainstream science. So I think that's one of the hurdles or challenges for us to overcome.
But let's rethink who it is that gives that reputation. So is that reputation with a certain journal? So who is the journal? Is the journal the publisher? Is the journal the editorial board? Or is it actually the community of scientists who are doing the review? If it's the community of scientists who are doing the review, but what is then the role of the journal? So it gets back to the question that the model of a journal is a response to the innovation of the printing press. So we have these two things. We have the goal of actually getting our science across. We have the goal of making sure that our scientific record is accurate. So that's what the reviewing system is good for. But actually the reviewing system not necessarily has to be attached to something that we call a scientific journal. So there are already platforms out where review is done independent of journals. There's the PubPeer system where you can share reviews freely, independent of journals. In fact, a problem with review as it's done at the moment is the process of the review is actually locked up. So we have a review process with valuable information that tells us something about the quality of the arguments, potential flaws, and this is all locked up. We don't see it anymore. We don't see the process anymore. Now think about open science. So there are several ways in which people tend to define open science. And my favorite one is actually, I like to characterize this open science means full transparency of the whole process of science. So that's how I would understand open. And in fact, through this peer review system, in order to make things better, we can actually see the quality of what is being done. Then we just look it up, and then we refer to citations to refer to quality. And in fact, citations are not a measure of quality of science. The reason why people started counting citations was because in about the 1950s, people were interested in figuring out what are current trends in science. What is trendy? What do people talk about? Where are the journals that have all this trendy stuff that people talk about? They were never intended to measure quality of science. People who don't understand anything about bibliometrics, who are not expert in the field, they started around the 1980s to think, no, it is a proxy for quality. And don't forget, yes, there is some correlation. Correlation does not mean a causation, and it's very important in this case that there's no causal relationship between citations and quality of research articles. In fact, what really drives up citations is actually things that are spectacularly wrong. And you find spectacularly wrong stuff throughout all journals, particularly the ones with a high journal impact factor. Because everything that is spectacularly wrong really drives up the journal impact factor. And the journal impact factor in particular is extremely sensitive to something that is spectacularly wrong, is completely blind to everything of lasting value.
Do you have, can you explain how journal impact factor is measured, roughly?
So there are two interesting things about journal impact factor. First, the journal impact factor only recognizes citations of articles within the first 2 years after publication. For the lasting value of any article, typically the first 5 years really don't matter. What matters for lasting value is what happens after 5 years, 10 years, 20 years. If they're still cited, and it doesn't matter how many times they're cited, it's a question of whether citations go up or down. So something that is spectacular at some time just bumps it up and then it decays very fast. So the other problem with the journal impact factor is the number of citations is a very skewed distribution across the articles in a journal. And it calculates the mean. And the mean is a very bad measure for a skewed distribution because it's very far from where most of the papers are. It's also not only there's a systematic problem about what it measures, but also in how it measures it. Further thoughts on the topic? So what is it that we should actually change?
So there are a couple of examples of somebody just switched us off. Yes. There are a few examples of ones. I want to go back to the point you raised about closing off the review process, because there are a few journals that actually run an open review process. And I know in South Africa with some of the telescope applications recently, we've experimented with double-blind peer review, which in a way is just the opposite side of the spectrum to a totally open peer review, where authors' names and reviewers' names and comments are all publicly visible. I can see pros and cons both ways, actually. Do you have any thoughts on that?
I mean, it's pretty much for that reason that I mentioned Wikipedia. Because I find it interesting to compare how it works and then think about what it is that we actually need, how we really would want to do this. Now we see a general problem here. That is how research is being assessed. And we're facing the problem that currently the way we do science is very strongly influenced by the way people are assessing it. That is, the assessment tail is wagging the science dog. And it should be the other way around. We should start with how we really want to do science, how science can best serve its purpose, and don't worry how it's being assessed. That's not our problem in the first place. And in fact, we're assessing far too much. There's the thought that everything gets better if we evaluate it. But maybe things get better if we evaluate less. And we actually spend our time on the science proper, rather than on these things. Now, there's another notion about this idea of a publication, because with the printing press, historically, this has to be something static. This has to be kind of end product. But actually, the scientific discourse goes on after something is published. So there's lots of discussion about review prior to publication versus review post-publication. So maybe it's worth thinking about that the scientific discourse is a continuous process. So we keep communicating, we keep debating, but we're kind of stuck, in particular with the way how research is assessed, with countable units, with countable static units. And that goes completely against all the sociology of how science actually evolves. And it has become worse. So if we go 100 years back, you see very nice discussions between Fritz Zwicky and Albert Einstein about how to do gravitational lensing of bodies. And it's a dialogue that's in the open. And you see very short articles. It's just half a printed page. No, Mr. Einstein said that, but I actually think this is the better idea. And they communicate with each other in the open. The whole theory of general relativity and special relativity, it's not one paper. It's a collection of something like 25, 26 different publications. And you can see the whole process, how the ideas evolved. I think it's quite a pain for modern historians of science, because we no longer see this process. And I'm now always pointing out to my students is we have to think more about the process of science rather than the end result. Because this is really how you learn science. You have to look at the processes, not just the results. You learn very little if you just see the outcomes of the research and don't see how you actually got there. And the development of special and general relativity is an absolutely beautiful process. We can see it in all details. We can see how Maxwell came up with Maxwell's equations, because they're also not designed at once. And I really don't understand why now people who write code about ethics use in a very polemic way the term salami slicing. Because I actually think that thinly sliced salami can be delicious. So there's not that much wrong with it. Are there any other thoughts, or should we wrap up?
Let me say something to wrap up, which is I think that I mean, as you've explained it now, Martin, you've said, let's put the process in public view. Let's have science open. Let's have the process of evaluating science open. And I think that has more benefits than just for scientists themselves, because once that process is open to the public, it means that, you know, it's accessible, it's understandable, and it really, I think, will also help to reframe the perspective of what science is in the public eye. It will help to counter things like misinformation and, you know, keeping stuff behind closed doors. So I think there's broader benefits to the public than just to the scientific community. So thanks very much for running this session and having this dialogue.
Testing one. Yeah. So that's what we want. Yeah. All right. Yeah. 111. 2. So if I want to make this louder, and then 1 1 1 1 2 2 2 2 2. Testing 1 1 1. Yeah, yeah. Uh-huh. Take 1 1 1. Yeah, 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 yeah. One, two, 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 1 1 1. 1 1 1.
来得及退出来，或者有的人干脆就走了，不管了，就干别的。
都有一个华为 MatePad 在这儿，live streaming，I'm gonna get out of here.
5点钟结束。